Hello everyone, it's Cadet Beckman here with Cadets VandenBrink and Pena, and we're here to share our findings from MAD 2, Parachute Dynamics. So the introduction. So the thing we're modeling is the free fall of a skydiver, and we're going to be modeling the position, velocity, and acceleration of the skydiver throughout their jump as they deploy their parachute. So the purpose of this is to understand how factors such as free fall velocities, landing impact speed, and changing drag coefficient of g-forces during parachute deployment play a role in how we are going to maximize or how we're going to effectively deploy a parachute. Doing this, we can understand practically how to minimize issues with late parachute deployments and how to best utilize a parachute during a free fall jump. And finally, the question we're going to answer at the big end of this is how high up would you fall from normal distance without a parachute in order to imitate a parachute landing. So the variables we're going to be using are, our independent variable is going to be time, t, and seconds since leaving the airplane. Dependent variables are going to be y, which is the vertical position in meters above the ground of the parachuter, v being the velocity in meters per second of the parachuter, a being the acceleration in meters per second squared of the parachuter.
The parameters we'll be using for this differential equation would be g, the acceleration due to gravity, which is simply given to us as 9.8 meters per second squared, and k to represent the coefficient of the skydiver parachute system, which represents the constant proportionality proportional to the square of the skydiver's velocity. Given from the drag equation. The assumptions we'll be making is that the increase from the drag in the parachute is instantaneous, so we don't have to account for any changes over time in that opposing force the skydiver experiences as he opens the parachute, and as well as the skydiver would be holding the same position the entire time in order to simplify our calculations. Given this, we would apply the fact that acceleration would be the derivative of its velocity, the skydiver's velocity, and the double derivative of his position. And from this ma plus the force of drag equals mg equation, we simply substitute a for v prime and y double prime respectively, giving us ODEs using velocity and position.
Alright, so to solve the differential equations, we used Mathematica to get y of t, v of t, and a of t, and then to solve for our hypothetical wall that we would have to jump off to get the same landing effect without a parachute, we took the final velocity that we would land with if we did have a parachute, which is the terminal velocity of our jumper with a parachute, and then we saw that it would take 0.58 seconds to reach that velocity if we were free falling, and then if our average velocity for that jump is VF plus VI over 2, that's 2.86 meters per second, and then 2.86 times the duration of the fall, which is 0.584, gives us a height of 1.67 meters. And then if we look at our solution graphs for the free fall, these solutions make sense because we see that he's when the jumper first jumps, the first part of the graph here, he's in free fall and the velocity is rapidly increasing, but then when the parachute is deployed and the drag coefficient instantaneously increases, the graph flattens out, and then velocity is constant for the rest of the jump as he falls to the ground. And we see this with the velocity graph as well, with the velocity being constant, and with the acceleration graph with a positive increase in acceleration for a moment, and then acceleration being 0 for the rest of the jump. And then we also see that with the static line jump, but the free fall is for a much shorter time with the static line. And with velocity and acceleration.
In conclusion, from this modeling, we would learn that a free fall jump from the given height from an airborne vessel of 1,219 meters would take about 170 seconds to complete, and a static line jump from 366 meters would take about 70 seconds to complete. And that the terminal velocity for a jumper with a parachute would be 5.72 meters per second, which would be the speed they reach the ground with. And if we wanted to find out the height of a wall, that's all we need to jump off of to hit the ground with the same speed. Using our physics kinematics equations, we calculated that the wall would need to be 1.67 meters tall. That would be our presentation. Our works cited. Thank you.